Okay, let's get started. A little late today. Having some technical difficulties. I'm not able to upload the answer key at the moment because it's on this computer and this computer doesn't have Ethernet. So we'll just sort of talk through the answer key and then I'll post it after class. So I'm sure you have all the questions memorized, but I don't. All right. So the first question pertains. I can actually bring up the paper probably. Yeah. All right. So the first question pertains to this figure here. So in their model, which of these things are exogenous, which are endogenous, which are known, which are unknown, etc. All right, got to go through this quick. What are the endogenous knowns? Andres.
SRD and RD.
Right, the two gray ones here, those are the phenomena we're trying to explain with our model. So they are endogenous to the model, but we can, if you threaten to sue the state of North Carolina for not following through with its open records law, obtain data on those. So those are knowable. Now, which of these remaining things, which are unknown, what are the ones that are exogenous? What are the ones that are endogenous? Someone besides Andres. Robert.
All of your mu's and sigmas on the outside are exogenous.
Okay, so the ones on the outside here, which don't have any arrows pointing into them. And then what about the ones in the middle?
I guess those are exogenous. I'm not good.
Rishika?
So all the mu's and sigmas which are drawn from formal exogenous unknowns, but the threshold and the lambda and t values wouldn't they be exogenous?
Endogenous. Unknown. Right. So this came up a little bit on Piazza. I think for the threshold ones and the FIDs that have arrows pointing into them, they're definitely unknown. Whether you call them exogenous or endogenous depends a little bit on your interpretation. I think both would be okay. In a manner of speaking, the model is trying to explain variations in thresholds. So in that sense, it's endogenous to the model. However, the explanation that the model provides for these is a very thin one. You could certainly elaborate a more detailed model that would maybe try to explain why the thresholds are different systematically in like rural areas than in urban areas or something like that. Here, the explanation is, you know, all the counties just kind of randomly differ from the North Carolina average. So it's not a real satisfying explanation, but in a manner of speaking, the model does try to explain the variation in these things. So I think you could say that's either known or unknown, or not. It's definitely unknown. Could call it exogenous, could call it endogenous, depending on whether it sort of satisfies your own threshold for an explanation. Okay, good. Question 2. What's an additional endogenous unknown of interest that could be computed if you knew the posterior distribution of all the variables in this graph? Salif.
Just kind of guessed, but I thought the prediction and future predictions of such very extent.
could use this to predict. So this was like data from 2009 to 2014. You could predict how many stops, searches, hits there would be in 2015, 2016, etc. Maybe if you can get data on those, you could validate your predictions. So yeah, that's a good answer. But there's certainly a good answer in the paper itself, albeit not in this graph. Rashika?
The probability of being searched and the probability of finding the hits, the probability.
So the probability of hits is sort of, yeah, directly a function of these things. But I mean, what is really like the thesis of the paper? It's the point it is trying to demonstrate. Robert.
I mean, it's trying to demonstrate that at least have different search thresholds for different
places. And so, like, to my mind, the most obvious endogenous unknown would be the difference in the thresholds for a particular department that they apply to white people versus they apply to minorities.
Isn't that already being estimated?
So you're getting the posterior distribution of these jointly, and if you want to calculate the difference, just subtract the white threshold from the black threshold or something like that,
yeah,
and compute that, then that is an additional quantity unknown. So the difference is not directly depicted here. It's just the levels. But that's really the legally important thing is, are you being consistent? But, you know, there's others that you could have put there for full credit. So the steps, again, you can't tell for sure just by reading the paper all the steps that they went through, because you're not allowed to like explain every little thing that you did in the course of writing a paper. But what are the steps that, you know, you definitely saw being reflected in the paper that we talked about last week is constituting the so-called Bayesian workflow, particularly a stand-centric Bayesian workflow. Becca.
So the first one, dividing the concepts, they do that.
Yes.
Although it's hard to figure out. They draw from the prior predictive distribution.
Quite likely, yeah.
Yes. We don't know. Even they maybe test the software. I think there's one note about testing some data at the beginning. So
Yeah.
Maybe. We don't know if they pre-register their analysis. I said probably.
They didn't mention it, and they probably would if they had.
They do obtain new data, or they obtain data. They use Bayes' rule to obtain the posterior.
Well, that.
Yeah, right. They draw from the posterior to assess. And I said that they sort of compare models, but not. It doesn't look like they compare Bayesian models. They compare like other models to this.
Mm-hmm.
They don't compare like multiple.
Yeah, pretty much. Like they did it a couple different ways, like 4 versus 6 or something, race category. Yeah, a little bit. I can see that definitely being a place where they would like have liked to put more in the paper, and the editors said like, you know, you got to stop. So yeah, you could see some of that. Maybe not as much as you would like to. Sebastian, you had a question?
Oh, yeah. I started on where they will use placebo treatment, where data we can.
Yeah, another way of investigating.
I thought this was almost being testing the model, where if you know, if different thresholds was sort of this automatic artifact of the model,
Mm-hmm.
where no matter what variable was assigning thresholds, if you just had something there always testing the different thresholds, we would have seen that. So it was a way of testing at least some of the model.
Yeah. Good.
Compared to the testing software.
Right. So overall, I think they followed it mostly. Certainly, pre-registering is not like a requirement. Some of the choices they made along the way, you might kind of see those as debatable. And if you don't pre-register your thing, there's always going to be somebody who said, well, you know, you didn't say you were going to exclude Native Americans from the whole analysis. Like, you could have done the analysis with Native Americans in, so I didn't support your, you know, point, and then taken them out, or, you know, something else that was kind of post hoc. I doubt very much of that went on. I somewhat suspect one of the reasons they didn't pre-register is because they thought it might make it more difficult to get North Carolina to give them the data if they knew what it was going to be used for. So that's like a countervailing thing. But anyway, there's nothing wrong with pre-registering your stuff, and it illustrates that you've thought through as much of the choices and decisions that you have to make before seeing the data as you can. And there's also nothing really wrong with deviating from your pre-registration plan as long as you make it clear which of the parts you plan to do in advance and which of the things occurred to you, you know, after you started playing with the data, things like that. So the third one, or fourth one, about writing out, drawing from the posterior predicted distribution. This is going to look easier when you can actually see the code, but that'll be up, you know, right after class. Basically, the steps that you needed to go through were to loop over the 4 races. Well, even before looping over the 4 races, there's some parameters like mu and sigma that are the hyperparameters there that are constant across races. So you can draw those from normal distributions. And then loop from 1 to 4, which is the number of races in the actual data that you have, and draw all the realizations of parameters ending in _r from their appropriate distributions. Those are mostly normal, 0, 2, sometimes with like an inverse logit or something in there if it had to be between 0 and 1. And then inside your loop from 1 to R, capital R, you need another loop over the districts. So they handle the first district, Charlotte, in a little bit of a different way. I'm not exactly sure why they choose to do that, but basically speaking, you need to loop from, you know, the start of the districts to the end of the districts. And inside that second loop, the interior loop, need to be drawing all the parameters, realizations of all the parameters that end in _D from their respective distributions. Again, tends to be normals, you know, something like that. And then third, interior to all that, you're going to need a loop from 1 up to the number of traffic stops by police members from Department D of cars driven by people of race R. And that is given by the stops integer array that you're passing to Stan. It has 100 rows for all the departments, 4 columns for each of the races, and each number interior to that is the number of traffic stops by that police department of cars driven by people of that race from 2009 to 2014. And so that's the total number of traffic stops. And then once you know that number, then there's a question, does the, you know, P, the sort of suspiciousness of the person parameter, exceed the threshold that people or that police departments are applying to people of that race? If it exceeds the threshold, then the model implies they're going to search the car. And if they search the car, the sort of suspicion probability threshold governs the probability that they actually find something illegal in the car and make an arrest. So there's pretty much 3 layers of looping over the races. That's the columns of stops. Over the departments, that's the rows of stops. And once you have the row and the column intersection, that tells you how many traffic stops there were that apply to that department and that race. And then you need to simulate the number of searches and the number of searches that allegedly find something illegal. Stick that into the first and second places in the out array, and then return that to R. Yes, Robert.
So I messed this up, but the ones that are not inside the loops are mu phi, sigma phi, mu lambda, and sigma lambda.
Yeah, the ones that don't have an R or a D subscript.
Okay.
Yeah,
So we
those.
draw ones for each of those, and then we draw phi d and lambda d.
Yeah, the race-specific ones, the department-specific ones. Yeah. Luke?
Yeah, so I don't understand why you erase this person, then the department.
You could do it the other way around.
Well, but could you also just erase your stuff in a vector? Could that do the same for the department, and then you redo and through both and the stuff?
Quite possibly. There's more than one way to skin a cat. You can definitely loop over the department's exterior and the race's interior. Since they handled the department one a little bit differently, to me it made most sense to loop over the race first. But yes, you can do 6 loops and store things in vectors and put them in the right place at the end. That's all fine, as long as it's consistent with the model implied by this graph with the elaborations that, you know, these things come from normal distributions, or our beliefs about them follow, you know, normal distributions or whatever it is. So what you said may very well be right or close to right. Andres?
You mentioned in the homework that one of the departments has like a value equals 1, like we assume it.
Yeah.
How does that enter into the code? Because I wasn't like, I didn't see
Yeah.
that.
So what they said was this thing, they restricted to be exactly 0 for Charlotte, which is the biggest department. I'm not entirely sure why. They had a footnote about it that didn't really make sense. But that's basically drawing from a normal distribution that has no variance just for that first department. And the rest of them, they had some unknown variance that, you know, you'd already drawn from. So I wouldn't get too caught up on that because I'm not even sure that was the most appropriate choice for them to make. But it didn't really fundamentally alter the model that you were ostensibly drawing from. Other questions about that without, you know, just going into way detail about the code? Sure, go ahead.
Maybe to briefly, same question I asked before this, right? Are mu TR and sigma TR, do you draw each of those once for each race, or do you draw them?
Yeah, so it's kind of weird because they end in R, but that's a double subscript. So it's not like they have one of these for whites and one of these for blacks.
Oh, okay. That's,
yeah.
That's
but you know, this is obviously specific to the race and the district.
Okay, it's confusing because it says race-specific hyperparameters of UTR and sigma TR.
Yeah.
It sound like they're different for each race.
It's not the worst thing in the world. You could have done it, you know, either way. I think from this picture, that's kind of why I interpreted it the way I did. But, you know, there's room to disagree about the interpretation of models. But this one in particular are ones that are written by people who are interested in estimating them with Bayesian techniques, tend to have more of the I's dotted and the T's crossed than sort of purely theoretical model papers that just kind of do some math, and or papers that are going to be estimated by frequentist methods where they just kind of in words describe like the problem that they want to investigate, and then they kind of jump to estimating a logit model, and you're not really sure how the empirical stuff connects to a theoretical generative model of what they're talking about. So there were some like kind of weird choices, maybe a little bit of ambiguity as to what race specific means. But for the most part, this paper and other papers that actually specify a generative model are, you know, pretty detailed about all the pieces in the model. And when you think of this in terms of what's a generative model for the process, it forces you to think about, you know, all the pieces that might be going on. And so this was, you know, in part an exercise in writing code, but it's also an exercise in taking a paper on a social scientific topic, reading it, and understanding what the author's model is. So essentially a necessary and sufficient condition for you to say, I understand this model, is that you can represent the model in computer code. Now, it doesn't necessarily have to be Stan or R, but we might as well practice doing Stan because we're going to need it the rest of the semester. And a lot of people got tripped up for a long time on this question, but it wasn't so much about the Stan syntax or where to put semicolons or things like that. It was more like what to do. And that is, you know, a good process to go through to make sure you can carefully read a paper like this that uses advanced quantitative methods and understand what the model is. There's plenty of time to an opportunity to criticize a model after you make sure you fully understand what the model is. But, you know, just understanding what a model like this is or implies is sort of below the minimum of what we would expect and you should expect of yourself for graduate students in social science, particularly in quantitative programs. Ultimately, we want you to be able to do stuff like this for yourself in your research. But sort of a starting point / stumbling block along the way is being able to understand what other people who are just a little bit farther along than you in grad school are doing in a paper like this. Now, if you're in epidemiology, like whatever, understand Ebola or bowling or the Super Bowl or something like that. But if you're in the QMSS or you're in the political science department, you should be able to understand a paper like this. And you demonstrate that you understand it when you can draw from the prior predictive distribution of this model using computer code. And that's what this, you know, fourth question is really all about. And most of the questions that we're getting on Piazza are just like, how do I do the loops? And, you know, what goes where? That are really more about understanding what they're doing in this model than it was, you know, any particular thing about the Stan language. Like it could have said, you know, do it in R and it would have taken you equivalently long amount of time just to set it up. Okay. Rolling along. Okay, assume the function works. All right, so do the prior distributions that the authors used in this paper reflect a belief that the police in North Carolina are discriminatory or non-discriminatory, and how do you know? Rishika?
I guess Beth said that because the race parameters are derived from the same distribution across all races, and that fundamentally it assumes that they are not racist. However, the way that they are combining the parameters together to finally get the threshold accounts for the fact that there can be some bias, but they are fuzzy about where the bias comes from, race or
Yes, that sounded reasonable. So the prior distributions that they were using were the same for all 4 races. So in that sense, you know, they weren't assuming there to be racist practices by the police departments, but the distributions they were using had variance. So it's not as if they came into this saying they were sure that the thresholds for whites and blacks were the same in every department in North Carolina. So there's variance to that, and certainly if you have a moderate amount of data, the posterior distribution is going to be able to shift you off from these distributions, but the prior distributions did line up before seeing the data. So that is correct. And I wanted to make another point about that. Okay, but it illustrates that when you do something like this, the priors don't necessarily have to be your priors. I think the fact that they went to all this trouble to collect the data, I didn't ask, but I assume the authors went into it anticipating that they would find some unequal practices going on in North Carolina or any other southern state that they could get data from, or maybe other states too. So your priors don't necessarily have to reflect your beliefs, just someone's beliefs, maybe who you're trying to convince or trying to make a decision on your behalf. I mean, if you did a poll, certainly a majority, maybe closer to 60% or whatever, if you ask them, do you think the police in North Carolina operate in a race-blind fashion, a majority in the United States would say yes. There's high levels of trust in the police overall in the United States, particularly among white people. So this was a way of, I guess, saying, okay, our priors don't assume that there's racism going on, but they're weak enough to where it's easy to spot under our model once we get all this data. Yes, Nikhil.
Just curious, about this. When you're presenting a model, do you think graphical models is the best way to show it, or do you that's a little related?
I personally like these a lot. They're very popular in epidemiology and sociology, not so much in economics, not that much in political science, honestly. But just sort of, you got to supplement this with words. But I think this is not bad. Just saying, here's a link to my code, which draws from the prior predictive distribution. And explaining that in words, but giving a link to where it's actually explained in code. That is certainly good, at least among people who could, seriously attempt to replicate your work or whatever. We, I guess, focus more, and we'll talk about this in the coming weeks, about visually, graphical presentations of the posterior distribution. With the prior distribution, you can show that too, but you're mostly just sort of checking whether that makes sense according to your beliefs. And I think in this case, the priors that they used were actually a bit loose in the sense that you could draw, once from the prior predictive distribution, and it, comes up, it says like, all Hispanics, all searches, result in hits or something like that. A very polar result that seems, pretty implausible. So the priors, in this case that they used, certainly, I think, put too much probability on extreme things. And maybe they did that intentionally, but perhaps, a little bit more of, graphing their priors, may have helped. Okay, one theoretical criticism. Roland. Independence? Yes, certainly. So it could be the case that there's dependence across stops by the same police officer who just, camps out and just, starts giving tickets to everybody, but, does so in a neighborhood that, is mostly a minority or, something like that. I don't think they can get data at the individual police officer level, so that's not really their fault. But the state of North Carolina should have that data. And they could, do something along this where the grouping is not the police department, but rather the police officer. And that might be more helpful. Becca?
I guess this maybe is going back to your earlier point, but I wasn't sure why it had a hierarchical prior for department, but just a week prior for race, when conceivably, like, there is actually more available data on race because you could look at other states or something.
Could. And they do have a paper under review that looks at as many states as they can get data on, and then there's more hierarchy going on there. But yeah, definitely worth considering. Sebastian?
So thinking about sort of the chapter, the red book, you could have similar results for other factors in the right? So certain cars, certain vintages of cars, certain neighborhoods are all associated with race, and those could feed in as well. And then you have sort of this confounding issue. But then it might not be because also all these things are driven by race, right? So you could have officers that are going to particular neighborhoods because they are minority neighborhoods are going after certain types of like cars, certain types of cars because of race. So it's a little strange it's very hard to disentangle all these factors so you don't know which one's really causal, especially given that,
Yeah. And I mean, they kind of say that explicitly, given the data that they have, that these P's, the sort of suspicion of, something on the part of the police officer that get drawn for, every person are basically this, proxy for all omitted variables, then they're in their analysis. Certainly, the real data that like the state of North Carolina has and doesn't make available is going to have, geocodes and, more information than what is given to the public, so not to be able to like identify specific people and stuff like that. So yeah, these are good things to think about if you somehow had access to privileged data where you could push farther along in this direction.
Also, when you talk about discrimination, as far as if you ask about intention versus fact, right? Because if you're seeing this bias about fact,
it could be.
It doesn't matter if like that's what you care. It doesn't necessarily matter if you're going.
Yeah, it could be sort of like subliminal discrimination on the part of some officers in some police departments without them sort of, I don't know, having like malice or anything like that. It could emerge. You ideally would want to have policies or regulations or something like that to try to discourage it. But they certainly don't know what was going on in the police officer's head. Andres, did you have a criticism?
Well, it's like when we finish this example, I have a question about how to compare parameters vis-a-vis how frequent this with parameters.
Okay, yeah, we'll do that. We'll definitely do that. Luke?
So, something that me parameterizing age based on B, unity on B, and using P to basically find S is a little short because it's less observed by and that's related to
you're sort of
observed and reality are
assuming that the P that the authors use to decide if it's above the threshold is kind of the same P as the probability you have a dead body or something like that in your car. That's definitely a limitation. Anybody else? Maybe just one with the data that they had, but didn't necessarily do as much with it as you could. Marlene? So this was over 2009 to 2014, and that's maybe enough considering all the data that they have to maybe estimate some trends. Hopefully it's been, getting better. Could be worse. I don't know.
Generally, the idea that it could have been reactions and probably back to the product of these departments. These essentially. This isn't calculated.
Yeah. So to me, the big one is taking the number of stops by each department and of each race to be exogenous and known. Certainly, a lot of the civil rights, people and whatnot are concerned that people who are minorities are being traffic stopped at different rates or for lesser offenses or speeding 5 miles an hour or whatever, and they get stopped, whereas someone who is white might not be. And so ideally you would maybe want your model to explain or try to explain differences in stops in addition to searches given stops and hits given searches. Becca.
Yeah, Nicole just whispered, how would you do that? And then I was like, maybe I should ask you do it. Would it be like one of the priors in your model would be like a population? Or like you would
So you could use the census data to get, some sense of how many people at least were living in the, jurisdiction of each department. That obviously you can drive from one county to the next, but
like you could have a distribution of expected stops based on population.
Right. So a decent prior for the number of stops of each race in Charlotte would be the proportion of registered drivers in each race. Maybe not residents, but I don't know. Yeah. You could start with something like that. You had a question about?
Yeah. So I was wondering when seeing all these parameters, what exactly is the price Bayesian pays to add more parameters? Because in traditional statistics, you're losing degrees of freedom. At some point, you can add more parameters than you have data points. It seems to me like both concerns are different. Maybe it seems to me like you could go crazy adding parameters and that wouldn't change anything. But
all right. Yeah, so we're definitely going to talk about model comparison in a couple weeks. So when is your model basically overfitting the data? When would a simpler model be preferable? So we're definitely going to get to that. Just because I can't really let it go. It should be pointed out that according to frequentist principles, frequentism has literally nothing to say about this research project. If you take the parameters as given and you have the population, there's no probability, there's no room for probability. There's nothing you can say about how the estimates would differ from one sample of size n to another sample of size n when you have all the traffic stops that happened in North Carolina between 2009 and 2014. There's no other sample that could have been taken from this population that gives rise to the problem of, well, we could get different estimates from different samples, and is the difference big or small enough to say that this is statistically significant and all that. There's no sample at all here. And so there's, really nothing that frequentists could apply a frequentist estimator to and get anything useful from the frequentist perspective. But the real issue here is not, how do the estimates change from one sample to the next, particularly when you have the whole population. It's preposterous to take the parameters as given. The parameters are what we're trying to find out. And you can have all the data that you want on stops and hits and searches. You don't have any direct data on the thresholds that were being applied there. That is a parameter of your model that you don't know, but you want to update your beliefs about. And so in a situation like this, really the frequentists should admit that their tools are not designed for this problem. Their tools were designed for a really different era where the idea that you would have the entire population was just inconceivable. But with electronic records and stuff like that, it happens a fair amount today. And even if you don't have the whole population, there's a lot of times in the social sciences where you don't have a sample. You just have a pile of observations. Now, in some cases in the social sciences, you legitimately do have a sample. But a lot of times you don't. And in that case, the whole frequentist apparatus is really not designed for dealing with that problem. But the sort of problem that frequentists were originally, come up about was not with, complicated models and estimating, things about people and, stuff like this that's being talked about in this paper. They would do things like, what is the proportion of people who get stopped in 5 years? Or how many times does the typical person have their car pulled over in 5 years? Or things like that are just sort of simple means, simple proportions. And, at best, they would have a small sample of data on which to estimate those things. But they weren't really thinking about rich models of behavior of people. And so those frequentist methods were not really designed for something like this at all. Salif?
I always thought it was the other way around. I always thought we're happy if you have as much data as possible, of course, because if you have then you make your estimate about, for example, any rate, and that's you didn't say, okay, that's the true rate, but that's what's going on. But you are saying, for instance, the threshold can't be observed, so therefore that's not estimable in the frequentist perspective, and therefore they just take a parameter.
Right. So, I mean, the whole probability apparatus is conditional on the parameters, taking them as given, even though they don't actually have them. But if you say, okay, if I knew the parameters and I had the population, there's no question how would the estimates bounce around from one sample to the next if you have all the data that there is during that time. But all the data that there isn't sufficient on searches and hits and stops, is not sufficient for you to know with certainty what the thresholds were. And that's really the essential question. Is the same thresholds being applied to whites as other people? And so it's that's a very natural thing for a Bayesian to ask, what is our probability distribution of beliefs about these thresholds, given the data that we see, without really worrying about what would happen in a different sample of data that we don't have. Andres?
I've encountered the word superpopulation a lot in papers.
It's for super frequentism.
And it kind of seems like an ad hoc solution to exactly the same thing you're talking about, but is it a solution?
I would say it's more ad hoc than solution, but you could say it's an ad hoc solution. So you can consider North Carolina to be a sample type thing from the population of states. And, you could, say this is a sample of size 1 from the 50 states. But it's a bit ridiculous to have a sample of size 1, first of all, and then to try to make inferences about the whole country. But moreover, given everything we know about the differences between the South and the Midwest and, other things, to generalize from one southern state to, also include how the police in Idaho behave. I don't think it really would tell you that much reliably. Merlin?
I have the same argument but across time.
Yeah. So you could sort of say 2009 to 2014 is a slice of the available times. Certainly they didn't have electronic records going back to the 1960s or something like that, where it might have been even more interesting to investigate, questions like this for for disparities. Still, I wouldn't really consider 5 consecutive years and to be a sample, particularly if they're the most recent 5 years that you could get your hands on. That's not the same as doing like cluster sampling sort of things. But anyway, good things to think about. And also, you know, certainly the just data mining-ish approach of let's get as much data as we can and find interesting patterns in the data also wouldn't work in a situation like this for the reasons the authors outlined at the beginning, that, you know, you could have a situation in which the police are applying different thresholds, but the sort of proportion of hits among all searches turns out to be pretty similar across races, or the other way around, where the thresholds are the same, but you see, you know, some races having a higher hit rate than others, even though the thresholds were the same. And that's why you have to put some thought into a generative model for what's going on here, rather than just saying like, we can never know what's going on. All we can do is like make predictions, you know, as fast as we can. Okay, in the interest of time, I think I'm not going to go into detail about the second question. I'll post the solution definitely, and you can see if you have more questions about that. But it's basically just applying the rules of continuous probability to come up with a posterior distribution and a posterior expectation in a, you know, stylized case, simulated data and all that. But I think it's good to dwell on this, you know, first problem, because it was an interesting problem and an interesting paper. And, you know, if you read to the end of it, they use Stan to actually do the posterior updating. And so we want to talk for the rest of today about what Stan does and how it does what it does. So disclosure, we actually have like a lot of new people who signed up on YouTube. So I should emphasize that I'm an employee of Columbia. Columbia develops Stan. I also use Stan for business purposes. That creates the appearance of a conflict of interest that you should be aware of. Now I'm headed the wrong direction. So to review where we picked up last time, Metropolis Hastings was sort of the original MCMC thing. It was used in the Manhattan Project and actually written up in the Journal of Chemical Physics, but not that many statisticians were reading the Journal of Chemical Physics in the 1950s. And so it took decades before the rest of us realized the potential of the MCMC method. And so the Metropolis Hastings, relatively easy to use because it only requires the user to specify the numerator of Bayes' rule. And in the course of the workflow that we talked about, you already have to know what the numerator of Bayes' rule is in order for you to draw from the prior predictive distribution of something. But the real disadvantage of Metropolis Hastings is that a lot of proposals get rejected. And really only like 20–25%, if you're doing it right, of your proposals should be accepted. And that yields relatively big jumps and overall sort of reduces the autocorrelation in the dependent draws that you obtain from the posterior distribution. However, the jumps aren't really all that big. And the real Achilles heel of Metropolis Hastings is that if you go beyond 2 parameters to like 3 or 4, the idea that you can sort of blindly jump in 4 dimensions simultaneously and land in a good place with respect to the posterior kernel gets smaller and smaller. And so the only way that you can keep your acceptance rate stable as the number of parameters in your model grows is to make the width of your proposal jumping distribution smaller and smaller and smaller. And so then you're still accepting, you know, 22% of the jumps, but the jumps are not very big. And so as the number of parameters gets larger, the size of the jumps has to get smaller. In principle, Metropolis Hastings could work kind of well if the proposal distribution that you're using is very similar to the posterior distribution you're trying to sample from, then you could accept with a high probability and it would still be okay. However, sort of by definition, you don't know how to draw explicitly from your posterior distribution. That's why you're doing this MCMC stuff in the first place. And consequently, it seems insurmountable challenge to design a proposal distribution that would work really well for your posterior distribution. Gibbs sampling gets at this a little bit. It has the additional burden on the user that you have to figure out what the full conditional distributions are. So you write down the kernel, the numerator of base rule, and then you say, okay, I'm just looking at the first parameter. Everything else I'm going to take as given, hold constant, drop all those constants, look at what's remaining, the kernel involving the first parameter, and say, ooh, that's chi-squared, or ooh, that's beta, and be able to draw from those distributions. And if you can do that, then you're at least drawing from a distribution that's tailored to your posterior in one dimension. But the fact that you're conditioning on all the other parameters means the conditional variance is lower than the marginal variance. And so you're not being able to jump all that far on the first parameter, particularly if it's highly correlated with the other parameters, so that the conditional variance is small. And so it's sort of, if you can't jump the full marginal variance, it's going to take you multiple iterations to get all the way around the parameter space. But the biggest problem with Gibbs sampling is, well, what if you figure out these full conditional distributions and you don't recognize what the distribution is? Then you can't go, and say R norm or R beta or, whatever for distributions that you have an algorithm to draw for. If it's some no-named conditional distribution, then, Gibbs sampling is not going to work. You have to fall back to Metropolis or Slice or something else. And then that is really going to undermine the gains that you made from the gains in efficiency from trying to go to Gibbs sampling. Nicole?
Can you explain again why we care about how big the jumps are?
Right. So if the jumps are very small, then the autocorrelation is going to be very high. That autocorrelation coefficient is going to be like close to 1. And so that effective sample size, which was S divided by 1 plus the infinite sum of the autocorrelation things, if it's like 0.99, 0.98, you're adding all that up, you get a big positive number in the denominator. Your effective sample size gets lower, a lot lower, fast. And that means, you can spend a lot of time doing this and still not estimate the expectations that you're trying to get at with much precision. Marla.
That's the size of the jump effect. Cost.
No. It's really, no. We make small jumps because we have to, not because we have to mathematically, not because it's computationally expensive. We would want to make large jumps if we could do that well. Yeah, Sebastian.
We're still trying to do base rule. This is all these conversations about the algorithm to do this.
To draw from the posterior distribution. Yes, but it's not just like, I don't have a lot of patience, although there's a lot of impatient people out there on the internet. It's more about the sampling has to be efficient in order for the inferences to be reliable. So if you have like a S of 100,000 and an effective sample size of 23, then you're estimating the mean of this thing that you're interested in with the equivalent of 23 draws that are independent of each other. And, if you just have a few effective draws, you could just by chance overestimate or underestimate the true sort of posterior expectation that you're going for really easily. Also, the estimator, in other ways, their reliability can be compromised when your effective sample size is low. So we want to get that as high as we can. and that just sort of takes as long as it takes. We want the inferences to be reliable. That's the most important thing. So Gibbs sampling, also historically important, shouldn't be doing it today. Bugs was probably the biggest milestone for bringing these sorts of things to the social sciences and other fields. Made it easier for the user because the user didn't have to work out the full conditional distributions themselves and say, oh, that looks like a beta distribution or whatever. Bugs had pattern recognition built into it, and so it could recognize kernels for distributions that it knew how to draw from, and it would do that whenever it could. And it had some other things that it could fall back on when it didn't recognize the kernel that it was trying to draw from. But because it could most of the time be falling back to its like backup algorithm, it didn't really have a very good effective sample size. And you see, you know, papers from like 2000 where they said, you know, we did 1 million, S equals 1 million. And that wasn't nearly big enough in order to get the effective sample size up to something reasonable for estimating a substantively important thing about their posterior distribution. Was there a question? Yeah. Okay. So how does Stan compare to this? Like Metropolis Hastings, you only have to specify the numerator. Like Metropolis Hastings, but unlike Gibbs, the proposals for what the parameters should be next are made jointly rather than conditionally, and are conditional on the other parameters. It's still conditional on the past iteration because it's a Markov process. But it's not like we're doing a subset of it conditional on the other subset. So we don't have the problem of the conditional variance getting small because the proposals are joint. Unlike Metropolis Hastings, but like Gibbs, the proposals are always accepted. So you never stay in the same place for 2 consecutive iterations. Unlike Metropolis Hastings, like Gibbs sampling, you don't have to set any tuning parameters a lot of the time. There are some that are there, but Stan's auto-tuning mechanism will get you in the right place most of the time, or at least close. Unlike both of these, the effective sample size of Stan is pretty good. It's typically going to be at least 25%. It could actually be a little bit higher than the nominal number of draws from the posterior distribution. And so you can do this with much fewer iterations. So if you have like, you do S equals 1,000, but you're getting effective sample size, you know, 25% of that, well, okay, is 250 draws enough to reliably estimate the thing that you're trying to estimate to the precision you need it to? Oftentimes, yeah. But, you know, a lot of the time Stan can actually be, you know, much better than 25%. Unlike both of those, Stan will give you warning messages when it feels like something bad is happening. So don't ignore those. This is one of the biggest, like, it's a good thing about Stan that a lot of people are annoyed about Stan. It tells you when things are going wrong, as opposed to bugs or Metropolis that just go wrong silently. But people complain about the warning messages a lot. And unlike bugs, this is actually kind of a disadvantage. Stan does not permit you to do distributions that have discrete unknowns. Bugs actually allows that in its language, but it's very difficult for it to sample those things with enough efficiency. You really need continuous unknowns to get this to work well. So the readings for this week, a bit on the technical and not very social scientific side. Believe it or not, those were the less technical readings. This involves some stuff from physics, and so I'll try to give you a brief explanation of this. So instead of drawing from the posterior distribution that you think you're drawing from, you know, theta given y proportional to the prior and the likelihood, Stan is going to augment this with augment the position variables theta that you're substantively interested in with momentum variables phi that you're not interested in. So these phi variables are really just a catalyst. But Stan technically is going to sample from the joint posterior distribution of phi and theta given the data. And it's going to integrate out the phi parameters to leave you just with a posterior distribution of theta given y. So these catalyst momentum parameters phi don't enter the likelihood function. And so the data does not change your quote unquote beliefs about what those are. And so consequently, the posterior distribution of phi is the same as your prior distribution of phi. And the prior distribution is not even in your control. It's normal, mean 0, and the standard deviations of them are actually tuned in order to make the performance of Stan best. So you don't actually even choose the prior standard deviations or anything about the prior on phi. But because its posterior distribution is the same as the prior, because it doesn't enter the likelihood and is unaffected by the data, at each iteration of the MCMC process, we can just draw a realization of phi k from its normal distribution with mean 0 and whatever standard deviation. Now, the sense in which these are momentum variables is that when we draw realizations of those on the if iteration of the Markov chain process, then we use physics and these phi variables that provide momentum to push the theta parameters around the parameter space that we've defined, you know, real numbers or whatever. And this space has a topology like mountains and stuff that is defined. It's like a trough, not a mountain, because there's negation in there. But it's defined by the negative of the logarithm of the kernel of the posterior distribution. So there's negative signs here, but when you take the logarithm of a product, it becomes a sum, and then you negate it and whatever. So Stan actually multiplies by -1 for you. So you can just continue to think in terms of posterior kernel, but in logarithm units. Okay, so we have the momentum variables pushing the thing around. We have contours that are being defined by this log posterior kernel, and it moves around according to the physics in that system. And I will attempt, this might not work, to show you a demonstration of that. There's a file on Courseworks called hmc.r, which I will try to download. And then can I open you? Sure. Okay, and then I'm gonna need my X server. Oh! I'm going to need my backup X server. There's utilities. Terminable. Oh, there's X quartz. Go away. That's what I'm talking about. Okay, now I'm going to sign into the top secret QMSS. Come on. Did I spell that right? Ben at studio. Okay, not working. And this is not going to have a C++ compiler on it. Okay, you can try this at home. Yeah. All right. Well, anyway, if you run this, and I'll maybe try to talk about how to do it on Piazza, it will give you this three-dimensional plot that it's a bivariate drawing from a bivariate normal. So it has like x unknown, y unknown, and then the z-axis is the logarithm of the posterior kernel. So you get this three-dimensional, but it's negated like bowl sort of thing. And then you have a parameter, and you can see how it moves, and you recognize it as being sort of, you know, physics, like when it starts to go up a hill and then down a hill, it accelerates and it moves around all over the place. But that is probably easier done than said. How did that get super big here? Okay. Question? Yeah, Becca.
So just to clarify, the reason that you want to push theta around is to reduce the autocorrelation and have the
Right. So the location of theta at any instant in that process is a draw from the posterior distribution. The topology of this space multiplied by -1 is defined by your posterior kernel. So if it's going around this like bowl type thing, if the contours of the bowl are defined by your posterior distribution, where it is at any point in time is a draw. And the system, unlike the systems that you're probably familiar with, doesn't have friction. And so it could move indefinitely if you just give it some like wind to provide momentum. So if it moves around indefinitely, when do you stop? And so postdoc named Matt Hoffman, who was here a few years ago, proposed stopping when the theta particle or system of theta particles makes a U-turn and starts to come back the direction that it came from. And since it's coming back the direction that it came from, it already has footprints on the way there. So U-turn is never an efficient way to get anywhere. And so he proposed to stop the thing when the particle starts to U-turn, and that's why it's called no U-turn sampling. That is the variation of Hamiltonian Monte Carlo that is implemented in STAN. And so when it gets to the U-turn point, one of the footprints that it made along its trek through the parameter space is selected with probability proportional to the posterior kernel. And that's the realization of theta at the sth iteration. And then we go on to the next one, draw a new random momentum from the normal distribution, push the particle around again, stop when it makes a U-turn, select among the footprints of the places that it's been. And so that tends to reduce the autocorrelation, maybe even make it negative, because where the particle theta goes to depends way more on the shape of the posterior distribution than it does where you start. Because you can get pushed around to anywhere in it. And so you can go from like one side of the parameter space to the other side of the parameter space in one iteration or anywhere in between. And consequently, it gets less autocorrelation. So this is technically a continuous time process that we have to discretize in order to solve the system of ordinary differential equations that govern this Hamiltonian physics process approximately. The approximation is actually very good, but it requires a step size for these like small discrete jumps that we're making, although you can make a bunch of them in each one iteration. And so it has this step size parameter that is tuned for you during the warm-up phase of STAN, which by default is going to be the first half of the iterations. It sort of figures out what tuning parameters are going to work best, hopefully. Then you throw away the first half because that's not really a valid markup chain. And then you sort of freeze all the tuning parameters at whatever they are, continue on for another 1,000 or whatever iterations, keep those, and then hopefully those will have a high effective sample size and be really reliable for inference. Okay, there's a few more things that I wanted to talk about today, some of the warnings and stuff that you'll see with STAN, but we'll certainly encounter those and have plenty of time to talk about them. So I'll stop for today. The readings for next week are up here, so come take one. Next week is the only easy week the whole semester. But it's easier if you do the reading, definitely. So we'll start to do regression models, which hopefully most of you are already pretty familiar with, at least from a frequentist perspective. We'll use Stan to estimate them, but the Stan programs and stuff like that are already written. So all you have to do is basically say what regression model you want to estimate and give it your data, and you can use Stan to draw from the posterior distribution of the parameters. Still important to think about a generative model for what's going on in any particular situation, but you don't personally have to write your own Stan code in order to draw from the posterior distributions of these models, and that is explained a bit in this reading from Gelman's book. We had to make paper copies because the book has not been published yet, so he doesn't want electronic copies floating around. So don't make a copy for your friend, but do read your copy. Pick it up next week. Step.
Do you want to have a tutorial session next week?